In this video, we're going to discuss the difference between our standard Bohr model, which we also call the single electron or hydrogen model, versus what we're going to call the many electron model or our quantum mechanical model. Okay, so based on previous videos, this is kind of the idea of what we have for strontium. So let's kind of review this very quickly before we jump into the quantum mechanical model. So we learned how to calculate our protons, electrons, and neutrons, which tells us that there's going to be 38 protons and 50 neutrons inside the nucleus. But more specifically, today's lesson is about the electrons. Okay, so we have this electron configuration, which was a previous video as well. And we came up with 1s2, 2s2, 2p6, all the way down to 5s2. And what we learned is that this big number in front tells us the ring that it's on. So for example, on the second ring, we have 2 plus 6 electrons, and that's why there's 8 electrons on that second ring. The third ring has the 3s, the 3p, and the 3d. 2 plus 6 plus 10 is going to be 18. And this is kind of like the model that we have for the Bohr model. So we pretty much put all the electrons, regardless if it's 2s or 2p, we'd put it on the second ring. Same thing for the third ring. It doesn't matter if it's s, p, or d, all those electrons go on the same ring, okay? Because in the Bohr model, we're talking about orbits, okay? And that's how it's done. When we jump into the quantum mechanical model, you're going to find out that there is a difference between the 2s and the 2p. So let's jump into it in the quantum mechanical model and how it's different than the Bohr model that we started with. Okay, so what we're going to do is we're going to make an energy diagram, and each of the dashes represents an orbital. Now I want to remind you, these rings over here are orbits, and we're switching topics from orbits to orbitals. So I'm going to start with 1s, and this has the lowest energy, so it's going to be all the way down. Our y-axis is representing energy, and so we're going to label this as 1s, and there's 2 electrons. Now the way we're going to show electrons in this many electron model is with half arrows, and one of them is going to spin up and the other one is going to spin down. So this is basically saying we have 2 electrons in the 1s orbital, 2 electrons in the 1s orbital, and then you just keep going. Okay, the next level up is going to be the 2s, so I'm going to raise up my energy to put my dash, and I'm going to label it as 2s. Excuse me, I'm fighting a cold here. Now, the first electron comes in, you might say, oh, it's going to spin up. Believe it or not, it's just random. This first electron in here, it could spin up or it could spin down. However, the second one, when you double up an orbital, is going to spin in the opposite direction. You can never have 2 electrons in the same orbital spinning in the same direction. That can't happen. Okay? Then we jump into the 2p orbital. And you might say, oh my gosh, it's like if I only put 1 dash here, how am I going to place 6 electrons? Well, the p orbitals are actually dumbbell shaped, okay, or 2 lobes in a node, okay. And here's a picture of all the different orbitals, which include s, p, d, and f. And as you can see, if you look at the p orbitals, okay, there's 3 orientations. One is along the x-axis, the other along the y-axis, and the other one along the z-axis. So even though those p orbitals look the same, they're oriented on different axes, the x, y, and z. So I'm going to do 3 dashes for the x, y, and z. And we're putting them all at the same energy level because they're degenerate. That's going to be a vocabulary word that we have, degenerate. And what degenerate means is that they have the same energy. Okay. Now, we're going to place 6 electrons in here. The first electron that comes in, it does not care which orbital it goes in because they're degenerate. They all have the same energy. So maybe I'll pick this third one, okay? And it can spin up or spin down. Let's say it spins up, okay? That was completely random, okay? Now the next electrons that come in, okay, have some rules and some randomness, okay? One of the rules it's going to have is that it's going to spin in the same direction in one of the empty orbitals, okay? So it has to choose either this first orbital or the second orbital. Let's say I pick the first, but it's going to have to spin in the same direction, okay? And now the third electron that comes in, it's kind of locked in. It's going to have to pick the empty orbital, because if there's one that's empty, it's going to pick it, okay? And then it has to match the spin of the other two. And we call this Hund's rule. And Hund's rule states that electrons will spin in the same direction in degenerate orbitals in order to obtain the lowest possible energy, of which we call a ground state, okay? So all these electrons are going to spin the same direction in these degenerate or equal energy orbitals. Fourth electron that comes in, it's going to have to spin down because now we're doubling them up. And remember, you can't put two electrons spinning in the same direction in the same orbital. So the fourth electron that comes in, it can pick any one of these degenerate orbitals. It just has to spin down. I'm going to pick the middle one. Okay, it's going to spin down. And I think you're starting to see the pattern. The next two electrons that come in are also going to spin down. It's going to pick one of these orbitals, maybe this one, and then this one. So what this diagram is saying right now is that I have 6 electrons in the 2p orbital. 6 electrons in the 2p orbital. And I always have at this time students that'll ask me the question, well, Mr. Hoeffel, like how will you know how I place those electrons in there on the test if it's just going to be filled up anyways? And the answer is I really don't know for these core electrons. I will find out, however, when you get to the valence electrons and at the last part of our electron configuration. That's when I'm going to find out if you're filling them in the right way or not. And I'll give a couple examples as we build on our atom, okay? So after 2p is going to be 3s. 3s is going to be a little bit higher. There are 2 electrons, a spin up and a spin down. The 3p, remember, p orbitals have 3 dashes. And when they start to fill in, like if I was asking a question where I only had 3 electrons, I would find out if you're filling them in the right way, because you can either spin them all up or spin them all down. Those are the only 2 options, okay? And that's how I would grade to see if you were filling them in the right way or not, okay? So I got these 3 degenerate orbitals in the 3p, and I got to put 6 electrons in. So maybe I'll do this quickly and just say, hey, we're going to spin them all up, and then we're going to come back and pair them up. That would be perfectly fine, okay? And like I said, if I made you stop halfway for the problem, that's how to find out if you're doing it right or not. After 3p is going to be the 4s. Spin up, spin down. Now I get to the 3d, okay? The D block on the periodic table has 10 columns, okay? And if you look at the D orbitals, you're going to see that there's 5 different pictures, okay? That's because there's 5 different orbitals for the D block. If they each hold 2 electrons, then they could hold 10 electrons. And typically, a lot of times, if we're filling up the D block, it fills up to 10, no higher than 10 for the D block. So whenever I'm doing this for the D, I'm going to put 5 dashes. Whenever I do P, it's 3 dashes. Whenever I do S's, it's just 1 dash. And those are kind of the rules in this quantum mechanical model. Now, I am going to fill up it all the way up to 10 electrons, okay? So the first one that comes in is completely random. Maybe I'm going to put it in that 4th orbital spinning down. As soon as that's established, now I have some rules that I have to abide by, okay? The next 4 electrons have to spin in the same direction, but they're going to pick these empty degenerate orbitals. Maybe this one, and then maybe this one, and then maybe this one, and then maybe this one, okay? But they're all going to spin in the same direction according to Hund's rule in their degenerate orbitals in order to obtain the lowest possible energy. The next 5 electrons are obviously going to spin in the same direction, going up until the whole 3D orbital is filled. Okay, so 3D 10. Okay, then I have 4p6, Okay, so this is the 4p. It's going to fill up. And then the 5s only has 2, and it's going to be filled up as well. So this is kind of like what the quantum mechanical model looks like for an energy diagram. Remember, these half arrows are representing electrons, okay? And the dashes are representing orbitals. So these 2 electrons in the 1s means I have 2 electrons in this 1s orbital, okay? Now, how is this different than the Bohr model, okay? I did a Bohr model energy diagram because in the Bohr model, if you have the 2s and the 2p, which has 2 and 6 electrons respectively, we just put all 8 electrons at the same energy level. So they're all on the same orbit, okay? So really, if it's 2s or 2p, the energy is exactly the same. Because remember, energy is on our y-axis, okay? So, and you can see all the 3s go together. All the 4s go together. In the quantum mechanical model, there's a difference in energy between the 2s and the 2p, okay? Now, what does that provide us? It provides us different jumps in which the electrons can go. In this strontium model, the 5s can only jump down to 4, 3, 2, or 1 because the 2s and the 2p are exactly the same. So it's just like 4 options that this 5s electron can jump down to if it's going to release some energy as a photon, okay? Where this 5s, it can have this jump, this, so 1, 2, 3, 4, 5, 6, 7, 8 different possibilities versus this 5s has 1 possibility, 2 possibility, 3 possibility, only 4 possibilities, okay? So the many electron model is a little bit more descriptive, and I want to remind you from our lesson the other day that when an electron jumps from one level to another level, it releases energy. And that energy has a particular frequency. And that frequency has a particular wavelength. And that wavelength might have a particular color in the visible region, okay? Or on a different part of the electromagnetic spectrum. So if we only have the Bohr model with these specific energy levels, okay, you're being really locked in to like maybe only like 4 colors. I think it's 2 purple, a blue, and a red color that you'd get as photons, okay? Where with the many electron model, okay, with these orbitals at all these different energies, really it's endless with the possibilities, okay? In addition, the 1s, the orbital that's closest to the nucleus in the many electron model is not always in the same energy level based on how many protons there are. For example, at the top of the periodic table, this 1s electron would only be attracted by 1 proton in hydrogen, okay? So it's not super close to the nucleus as compared to maybe something like barium that has 56 protons that are really attracting this orbital close to it, so it's a lower energy than maybe something like hydrogen. So once again, the quantum mechanical model kind of endless in the possibilities between these jumps of electrons. Okay, so that's the comparison between the Bohr model and the quantum mechanical model. I now want to switch gears and talk about some vocabulary words that's specifically for quantum mechanics. So I'm going to move my camera just a little bit. And we're doing that so we can focus in on some vocabulary words with quantum mechanics. Okay, there's going to be 4 numbers that are going to be used to describe one of these particular electrons in our energy diagram. So the letters are going to be N, L, M sub L, and M sub S. And we're going to write down numbers for each of these. But I do want to describe what each of these things mean. So the N is what we call the principal quantum number. Believe it or not, we've seen N a lot already. This is N, this is N, this is N, this is N. So these big numbers in front are what we call the principal quantum number. And the principal quantum number is going to tell us two things. It's going to tell us the distance from the nucleus, and it's also going to tell us the energy of the electron. So as the principal quantum number increases, the electrons get further away from the nucleus, and therefore those electrons tend to have more energy. Remember, the things that's really attracted to the electrons is like the 1s. They're going to have the lowest energy, and they're going to be the most stable because electrons, which are negative, are attracted to a nucleus that is positive. Okay, so as n increases, the orbitals get further away from the nucleus and they have more energy. The L is what we call the angular momentum quantum number, and it's going to tell you the shape of the orbital. And I've already showed you some shapes here. I'll hold it up again. You know, your S is going to be spherical. Your P's are going to be what we call a dumbbell, or two lobes in a node. And those are the only ones that most schools kind of make you kind of like understand. But that D, it's going to be like four leaf clovers. One looks like a donut. And then you have the F's, which are kind of like, there's more lobes on the F than the D. I think like six to eight lobes. And there's another one that's like a double donut as well. And so they're going to tell you the shape of the electron cloud is what L tells you. And there's a code for L as well. So I'm going to write this down. S is equal to 0. P is equal to 1. D is equal to 2. And F is equal to 3. And this is the way that you do electron configuration. So you hit your S's first, which is zeros. These P's are going to be 1s. And then we get to D, which is going to be 2. And then if we eventually got to the F block, F would be equal to 3. Okay, so 0, 1, 2, 3, S, P, D, F. Okay, the next thing is going to be your magnetic number. And the magnetic number tells you which orbital it's going to be in. Okay, to make this easy for you, we arbitrarily assign the middle one 0. And then we treat it like a number line where negatives are on the left and positives are on the right, and we do it by integer. So that's going to be a -1, okay? And this is going to be a +1, okay? If we're just dealing with S's, all the S's are going to have a magnetic quantum number of 0 because there's only one dash, okay? If we're talking about the D's, okay, remember the middle one is going to be 0. And then we got -1 and -2. We got +1 and +2 for our magnetic numbers, okay? So once again, let's kind of quickly review. N is the big numbers, okay, which is called the principal quantum number. L has a code of 0, 1, 2, and 3 for S, P, and D, and F. So S's are 0s, P's are 1, and D's are 2, okay? And then we have the magnetic number, which tells you which of the orbitals it is. And then finally, we have our spin quantum number, which is either +1/2 or -1/2. And that is equal to clockwise and counterclockwise spin, okay? So +1/2 is going to be our spin up, and our -1/2 is going to be our spin down. And what we're trying to do is I'm going to try to give you a set of quantum numbers, and then you should be able to pick out one particular electron in our quantum mechanical model, which is described kind of like as an energy diagram for the electrons right now. So let's try to do a couple examples. We'll try to do 2 examples here. Let's say I have the quantum numbers of 2, 1, -1, +1/2. If these are my quantum numbers, if it's the principal quantum number of 2 for N, this narrows it down to 8 electrons. It could be either the 2 electrons in the 2s or the 6 electrons in the 2p, because the only thing that has a principal quantum number of 2 is the 2s and the 2p. Not the 3s's, not the 3d's, not the 4p or the 5s, just the 2s or the 2p have a principal quantum number of 2. The L, which is equal to 1, remember there's a code for that. So L that's equal to 1 means it's the p electrons. So this is actually saying 2p. So this part right here is telling me 2p. So it's going to be one of these 6 electrons. Okay. The next piece is the magnetic quantum number, and that's going to tell you which of the orbitals. It's telling me -1. So I'm going to come down here and fill in those numbers like I just did. So if we're talking about the 2p, and it's at the -1 dash, we're talking about one of these 2 electrons. And then if it's +1/2, okay, that means it's going to spin up. So we're talking about this particular electron right here. So kind of that guy right there has the numbers of 2, 1, -1, +1/2. Okay, so we can use these quantum numbers to find a particular electron in an atom, which is kind of like just like blows my mind a little bit. Okay, let's try this one more time with a different set of quantum numbers, and we'll call it a day on our quantum mechanical model. Okay, let's say we had a 3, 2, +1, and -1/2. Let's see if you can find that electron in this model. Okay, the first number is 3, so that means we're talking about the 3s, the 3p, or the 3d. So just from this 3, I have it narrowed down to 18 electrons, 10 from the 3d, 6 more from the 3p, and 2 more from the 3s, which totals to about 18 electrons. Now the 2 is the L, and there's a code for that. So the L, that's a 2. That means we're talking about 3d. So these two numbers together are telling us, hey, we're in the 3d. So that means we're somewhere in here in these 10 electrons. The next number tells us which of the orbitals it is. So it's going to be one of these 2. Okay. And it says -1/2. So if we're at the 3d, the +1 with a -1/2, we're talking about that electron right there. That's the electron that has 3, 2, +1, -1/2. So we use this to kind of discuss the quantum mechanical model of the electrons and to understand some of these vocabulary words. And as we continue our study, we're going to dive a little bit deeper into the relationships between N, L, M sub L, and M sub S. Okay, but I hope this video was helpful, and if you did find it helpful, please like and subscribe and share it with your friends. I want to get this out to as many chemistry students that are having a hard time, that kind of want an easy and simple way of understanding chemistry.